Good afternoon, everyone. I hope that are having a good start to your Tuesday. I hope that you've had a good morning so far. Um, I have not finished with the grades for your exams, and I will get those posted this evening. I'll also release the key so that you have the correct answers. Um, and I haven't done it because I'm just working on some other things, and I know that it's a high priority for you guys. It is. It just isn't. It has not become the highest priority for me. I'm trying to get other stuff for this week's class squared away. But like I said, I will have the exam grades posted this evening. I'll give you some uh, of the results on that as well. Now, with that in mind, one of the things that I wanted to mention, because I had somebody who I met with yesterday in class, and um, they seemed a little bit stressed about their performance. And one of the things that I wanted to bring up was, and I know that I mentioned this on like the first day of class, and then I talked to some folks along the way about it. But over the course of the semester, you will continue to have the opportunity to basically improve your grade. And what I mean by that is the score that you get on exam number two. If you do better on exam number two than you did on exam number one, then that will replace your exam number one score. Um, then the final exam is also an opportunity to replace all of your exams. So, what I want you to do with that information is I want you to look at exam number one whenever you get access to it. I want you to very critically look at the questions and say, can I classify these questions? Did I get this question right because I knew it? Or did I get this question wrong because I had no clue? Did I just guess on this? And basically try to identify, like, is there a skill that was in each one of these questions that I understood or did not understood? And then, did I just like flip a coin and I picked the wrong one? Um, so that's one of the things that I think will be very important for exam number two and your final exam. But most immediately exam number two, because exam number one material, so like amino acids, PI calculation, that's going to be on exam number two. There's going to be, of the 40 questions that constitute exam number two, about 10 of them will cover material from exam number one. Um, and so with that, I'm going to go ahead and forge ahead. If anyone wants to meet with me, um, either hang around for a couple minutes after class, I'm glad to do that. If you want to, after or this evening, after you have had a chance to look at your exam score, um, you know, maybe we wait till then. But that's that. Um, One reminder for this week is that the Thursday and Friday classes will be available, or they are going to be pre-recorded. What that most immediately impacts you guys on is I will not have office hours on Thursday. I'm going to have office hours tomorrow instead. Um, but then if there's something that comes up over the weekend or something like that, email me and I'll get back to you. If you want to join a Zoom meeting on the weekend or something like that, I can do that. Um, our next exam is on Monday. So there's such a quick turnaround in the summer, but that's what we got. Then before I proceed, yeah, quick turnaround exams. Um, Yeah, I think that's everything. I've got my chat window open, so if anyone has any questions or anything like that, you can send me a private message or um, there we go. Your problem set number three is up, and I've got that set to be due on Friday. And the reason that I have it due on Friday night is because um, I wanted to give everyone the chance to basically have you know, adequate time to get response, or sorry, adequate time to submit it before the exam. I think what I'm going to do is I'm going to push it to Sunday. And then immediately after that, after that submission deadline. Um, so at like 12 a.m., the key for that will pop up, so you'll have that to look at as a reference. We have a quiz on Thursday, and I keep that on Thursday though. And that's same thing as the last time, open between 12 a.m. or 12 p.m. and 11:59 p.m. And I'll send some suggestions on what you can do to study for that quiz. Um, and there we go. Okay, so enzymes. We started with a talk or a discussion of enzymes the other day, but we cut it off in advance of our exam. Um, this week, our material for the upcoming exam is going to be um, enzymes, nucleic acids, and sugars. So that's a lot of material. I've started and all those PowerPoints are up for this week. So if you want to kind of browse ahead, you're more than welcome to. I don't think that we're going to have a problem getting through it all, though. So unlike last week where I stopped a little bit abruptly, I don't think that's going to be an issue for this week. But today and tomorrow are a little bit dense. So if after today's lecture you want to go ahead and browse ahead, go for it. With that said, enzymatic reactions, what do they do? First and foremost, they lower the activation energy of a reaction. They catalyze reversible reactions. So just as an enzyme can catalyze and speed up a reaction in one direction, it can go the exact opposite direction as well. They do not change the overall free energy. They just focus on the activation energy. They do not change the equilibrium concentrations or constant. So those remain the same. Um, enzymes, their speed is it helps us reach equilibrium a little bit faster. Now, if we think about an enzymatic reaction as reactant A going to product B, that's a good place to start. Okay, A goes to B. If you like other kind of representations, like a circle is converted to a square, done. At equilibrium. So our um, substrate or our reactant A concentration is equal to our reaction 5 seconds later. So this is saying our concentration of a reactant at time 0 versus at time 5 seconds. We're at equilibrium, so nothing is going to change. Similarly, our product, B, the concentration of B is going to be unchanged over time if our reaction is at equilibrium. At any amount of time, X. So any amount of time from our initial point or our once we've reached equilibrium on into eternity, nothing's going to change. So that's what this expression is telling us. Equilibrium, nothing's going to change unless there's some sort of intervention of some sort. So our delta G, not prime 0, it's wrong to say that A is equal to B. So that's one of the misconceptions about equilibrium. And this goes back to kind of a Gen Chem 2 pieces of information where, well, your concentration of your reactants in your products are not equal. Instead, at equilibrium, your rate of your forward reaction is equal to the rate of your reverse reaction, in the sense that we've reached equilibrium. Just as much of a reactant's being converted to a product's being converted to a reactant. But the concentrations of those two things, the reactant and the product, they are not going to be equal to one another. Now, when it comes to enzyme catalyzed reactions, one of the big things that we're interested in and what we want to study as biochemists is we want to study substrate binding. The reason that we want to study substrate binding is because substrates are something that we can manage a little bit better. And by that, I mean, you can control that variable much better than you can control enzymes concentration. So whenever we talk about substrate binding, we are interested in the makeup of a reaction. There is one type of reaction, or a reaction can be a single substrate is converted to a single product. A gets converted to B. Fantastic. Great. Circle goes to reversibly square. And then square reversibly goes to circle. Okay. Another option is, well, a single substrate is converted to multiple products. So here, I like visuals, so I'm going to do that. If you don't like visuals, I'm sorry. I hope that this doesn't anger you. This circle is cut in half. 2 half circles, 2 semicircles. Done. Multiple substrates. Well, this would be kind of the opposite of this right here, where we have two reactants coming together to make a singular product. Now, where it gets a little bit more complicated is where we have multiple substrates and multiple products, where we have two reactants going to make two products. I think that these first three, it's a little bit, it's kind of something that's easy to consume and it's easy to follow because, you know, whenever I look at a single substrate is converted to a single product, there's a word that comes to mind and it starts with the letter I. Can anyone finish that word and add it to the chat? And yes, I'm asking a very directed question, but whenever I say the answer, you're going to say it or you're going to know it. I'll give you another hint. The next letter is S. The next letter is O. Close. I'm going for isomerization. See, that was a very, very targeted question that I knew the answer to, and I was like, that's a good question. And that may or may not have resonated. But isomerization, you're not doing anything to remove any parts of that. Instead, you have, uh, we'll just go with an organic molecule like 3-butanol is, or 3-decanol, there we go, is converted to 2-decanol. It's the same molecule, same makeup of the atoms. Then if we talk about single substrate, multiple substrates, well, a decomposition reaction would be where a single substrate becomes multiple products, and then a synthesis reaction would be multiple substrates becoming a single product. Can I get a number if you follow those models for different reactions and a letter if you don't follow those? Okay. So I'm just providing you with an idea of, well, what are these types of reactions? So I want you to think about you've taken organic chemistry, you've taken Gen Chem 1, Gen Chem 2 models for reactions. So a multiple substrates would be like plus Cl minus makes NaCl. Now, is this a biochemical reaction that I'm stressing? No. I'm just trying to give you the context for, hey, you've seen a reaction very similar to this, but you just use different terminology. When you took Gen Chem 1, you called that a synthesis or a combination reaction. And then for that single substrate becoming multiple products in Gen Chem 1, you called that a decomposition reaction. These, however, these last few are multiple substrate reactions. These are a little bit more complicated. What makes them complicated is this is kind of uniquely enzyme driven. Okay. There are three different reactions, and I want you to know these models. So there is the ordered reaction, a random reaction, and a ping pong reaction. Okay. Now, these are the models that I want you to be a little bit familiar with. What I'm going to do is take a step back and go back to the previous slide and basically reconstruct some of these. So if we think about, or what I want you to know about is an ordered reaction. We've got an enzyme that we're going to identify with the single letter of E. And what E, the enzyme, can do is it can bind two different substrates. And let's call those substrates A and B. Okay, so our enzyme is a biological molecule and it binds A and B. And let's say hypothetically that A has a hydroxide group. B does not have a hydroxide group. What our enzyme is going to do is it's going to take on these two substrates, A and B, and it's going to make, well, it's going to return itself to E, but it's going to make A and B OH. So all that's happening here is our enzyme is binding A with the alcohol, and it's taking that alcohol off and putting it onto B. Now, my question for you is an answer with a letter if your answer is yes, and answer with a letter if your answer is no. Does this right here that I just circled, does that have the alcohol group anymore? A letter for yes and a number for no. No, it does not. You're absolutely right. So, should we really call it A anymore? Let's not call it A because our molecule with the alcohol that we called A, well, let's go ahead and call this C. Is everyone good with that? Okay. And now B with the alcohol, well, that's a little bit different. So rather than calling it B, we're going to call it D. These are just placeholders. We took two molecules, one with alcohol, one without, move the alcohol from one molecule to the other. Can I get a number if, okay, cool, I follow that? I follow the process. Okay. Now, what we are looking to do here is that's our overall reaction. The question is, does it matter? And let me rephrase that. Does the enzyme care, or does the enzyme need to bind one molecule before the other? And enzymes kind of have that preference. For instance, if I were an enzyme, I like to I like to eat a Twix bar before I take a nap. Do I have to eat that Twix bar before I eat the nap, or could I eat the Twix bar while I'm taking my nap? It's going to be kind of difficult to eat a Twix bar safely while I'm taking a nap. So there is a sequence that has to take place. So in an ordered sequential reaction, that's what this is known as, or an ordered ternary mechanism, our enzyme, represented as E, binds molecule A, forming this EA complex. When that EA complex has formed, so our substrate is interacting with our enzyme, then our second substrate, which we recognize as B, can bind. Then we can form EAB. That's an enzyme plus the substrates, and then EPQ. The P and Q are the two different products, respectively. Now, how does this, thinking about, well, how would this end up as a test question? One way that this would end up as a test question is I would say enzyme R, we'll say, binds substrates R, no, not R. We'll say substrates D and F. Those are our two substrates. D first, then F. Okay. So I've taken those letters and I've just rearranged them, giving you different examples. Our enzyme R will bind D, then it will bind F. My question is, will there ever be a RF complex? Answer with a number if you think the answer is yes, and answer with a letter if you think the answer is no. You're absolutely right, because we have to bind D before we bind F. So there will never be an instance where the enzyme will bind F and be able to catalyze this reaction. So that's an ordered ternary mechanism. Now, with an ordered ternary mechanism, something has to happen. There's a required sequence. Now, kind of the opposite to that is known as the random ternary mechanism. And I'm just going to use this. I'm going to, yeah, focus on. In this case, we've got our two substrates, A and B. And our enzyme is capable of either binding A, then binding B, in forming that EAB complex. If the EAB complex is kind of the enzyme's destination, well, it can bind A, then it can bind B, or alternatively, it can bind B, then it can bind A, still ending up with a complex right here that is required for catalyzing the reaction. Now, one way that you could think about that is it's like an enzyme is a molecule that moves. And if we were to come up with, let's say, just because I had these things on my desk or near my desk, my hand is the enzyme. I have a screw right here and I have my drill right here. If I were to, if my enzyme is catalyzing a random ternary mechanism, well, one thing that I could do is I could pick up the screw and then I could pick up the drill. Done. This is my EAB complex. I picked up the screw, then I picked up my drill. Alternatively, I could pick up my drill and then, well, that's ironic. I dropped the screw, but I could pick up the drill second. So the sequence does not matter for a random ternary mechanism. The sequence of events is not necessary and requisite for a random ternary mechanism. Now, what that means is our products can be released in a random order, whereas in an ordered ternary mechanism, the products are going to always be released in a particular sequence. Now, one thing that I want you to know about these EAB and EPQ, those are just representative letters. So those are just representing the enzyme and products and substrates. Now, does anyone have any questions about an ordered ternary mechanism or a random ternary mechanism? Okay. Now, our last mechanism, when it comes to sequence of events, is known as a ping pong ternary mechanism. Now, the ping pong ternary mechanism is a little bit different because what we have is we have this thing right here, F. Huh, that's a little bit odd. What is that? Well, if we look at what's below the line here, we have our enzyme, then we have our substrate come in, and we form our EA complex, enzyme and a substrate, and then we get FP. Now, before we proceed, answer with a letter for no and a number for yes. Right here, does our enzyme bind both of our substrates in a ping pong non-ternary mechanism? Sorry, a ping pong mechanism? No, it doesn't. It does not bind both substrates. What this is showing you right here, our enzyme binds to the substrate, then we get F, which is a new form of the enzyme, a different form of our enzyme. P is a product. That product is released, and then let me ask you this, again with a letter for no and a number for yes, is F the enzyme? Is F our enzyme? It is. It's our enzyme. Something about it has changed. Now, think about it like this. We have our enzyme, we have our substrate. We have our first product right here. What's left behind is F. That is our free enzyme. But what is different about it is something came from our first substrate and is added to our enzyme to make it slightly different. So the chemical composition of our enzyme has changed. Now, to visualize that, here's what one of those reactions will look like. I want you to start over here with our line. And we're going to jump from this point to this point. The enzyme is the same as from when it begins until when it ends. It's still the enzyme. The first thing that this enzyme is going to do is bind this molecule right here. That's aspartate. It's an amino acid. We've seen that before. Okay, so this is an enzyme that binds aspartate, and this, what I've circled right here, is our alpha carbon. Here's our R group. Okay, cool. Now, what this enzyme is going to do is it's going to take that aspartate, that aspartic acid, and it is going to remove this NH3. And what's going to happen is this is going to be ENH3. So our enzyme has taken on an NH3. So it's an extra NH3. So you could kind of say that it's an aminated, not animated, aminated enzyme. Where did that amino group come from? Add it to the chat, somebody. To make our aminated enzyme, where did our amino group come from? Aspartate. You're absolutely right. So our enzyme basically grabbed that amino group and added it to itself. So answer with a number of is E equal to ENH3? Question mark? No, it's not the same thing. So that's why this ENH3 is effectively this right here, that F, that different form of our enzyme. Now, what's going to happen is that amino group that's added to our enzyme is going to then be used and transferred onto another molecule. So what's going to happen is our second substrate, in this case, it's represented as B. B binds to F, which is our aminated enzyme. Then that amine group is transferred from the enzyme, F, to our second substrate, which releases our second product. So essentially, what's taking place is our enzyme is binding to aspartate, taking an amine, releasing the remainder of aspartate, and then it sees another molecule come by and says, okay, cool, well, I'll add an amine onto you because I got an extra one, and now you can go on. So it's effectively transferring an amino group from one enzyme to another enzyme, one amino group, or an amino group from one molecule to another molecule. Okay, does everyone follow, or does anyone have any questions about the ping pong non-ternary mechanism? Can I get a number if you feel comfortable with an ordered, random, and a ping pong mechanism? Number if yes, and a letter if no. Okay. So at its heart, when we're thinking about these different mechanisms, the question is, does the enzyme form a different form, or does it take on like a different form? If the answer is yes to that question, it's a ping pong mechanism. Then your next question is, well, does it matter which substrate binds first? Can it bind substrate A or substrate B first? If it is flexible, then it's a random ternary mechanism. If, however, it has to go in a very regimented specific sequence, that is an ordered ternary mechanism. Okay, great. Now we will proceed from there. So another way of looking at that is one enzyme known as lactate dehydrogenase. This is an enzyme that utilizes pyruvate. Pyruvate is one of the compounds that is generated from sugar metabolism, your anaerobic sugar metabolism. Pyruvate and NADH will produce lactate and NAD+. This follows an ordered mechanism. NADH must bind before lactate dehydrogenase binds pyruvate. I'm not expecting you to or wanting you to know this specific example, but I'm just trying to give you kind of an application. Creatine kinase, if anyone's ever taken the dietary supplement creatine, well, then you have tried to get creatine kinase to be a more active enzyme and produce a little bit more of this compound right here, or this molecule creatine phosphate, so that you have a readily available kind of secondary store of ATP. Creatine kinase goes reversibly to bind creatine and ATP to make creatine phosphate and ADP. When you have lots of creatine phosphate in your cells, well, then you can more actively fuel ATP stores. This enzyme, creatine kinase, does not care. It is not selective at all. So this would be, there's no order to it. So this would be a random ternary mechanism. So ordered and random are our two mechanisms there. Now, this previous one of the ping pong mechanism, there's a large number of examples of those, and I kind of showed you the one with the binding of an amino acid, transferring an amine from one molecule to another, with holding on to it or binding it to itself as the intermediary. Now, this is more of a representation of that, where we have a transaminase, where what's happening is that amino group is being transferred ultimately to another molecule, but in the interim, it's binding to itself. So what I want you to do over these few slides is understand kind of the process that's taking place. This is another representation of a ping pong mechanism. Now, here what we have is our enzyme. So substrate 1, product 1, and then our substrate binds to our enzyme, and then we're going to transfer that amino group onto our other molecule. The enzyme is going to flip between two different states. So this NH2 is transferred from our enzyme onto our substrate number 1. Sorry, this is 1. This is our enzyme deaminated. Then our enzyme is going to pick up our substrate 2 so that I can take this amine from our second substrate to return our enzyme right here to its original state. So it can go back and do this over and over again. Okay. Now, does anyone have any questions about those mechanisms? If so, please let me know. But those are the 3. These are just a couple of different ways to visualize them. Now, at the heart of study of enzymes, it's important to know how many substrates an enzyme has. It's important to know the sequence that it's going in. But one of the important things, or one of the most important things that we're interested when it comes to an enzyme, is we want to know how fast can an enzyme catalyze a reaction, and we want to know how much does an enzyme need? How much substrate does an enzyme need? Now, this graph right here is kind of an important, albeit sort of complicated one. What I want you to do is look at the y-axis. That is a general measure of concentration. It is not identifying a specific thing that we're looking at the concentration of. And the reason for that is we have these 4 different lines that we're looking at the concentration of different things. We've got, first of all, our substrate concentration. represented by this black line. Could anyone tell me in the chat what happens to our substrate concentration as we move from the left-hand side of our graph to the right-hand side of our graph, or as time proceeds? It decreases. Okay, so think about a substrate as a necessary reagent. If an enzyme is consuming that substrate, does it make sense that our substrate concentration decreases over time? Give me a number for yes or a letter for no. That does not make sense. Absolutely. We're expecting that our substrate is going to be consumed over time. Now, what do we expect? If our substrate is consumed over time, what do we expect the concentration of will increase? We expect something's concentration will increase over time, kind of in relation to that substrate. What is that thing that we expect to see increase in concentration over time? Substrate goes down, our product. We have our input of our substrate and our output of our product. We expect those two things to almost go hand in hand with one another. And if you look at this red line, which represents our product, sure enough, that seems to be what's happening. At some point, though, they're both kind of tapering off a little bit. Then we have two other variables, our enzyme concentration and our ES. Our ES is our enzyme substrate complex. Okay, so we've got our free enzyme concentration and our enzyme substrate concentration. And if we look at our free enzyme concentration, it goes down, then it goes back up, and then it kind of plateaus. Our enzyme substrate concentration starts low, goes up, and then it begins to plateau. So over time, I mean, what is another way that we could, do you think that that enzyme line, that enzyme concentration line, do you think that's going to flatten out? A number for yes, a letter for no. I'm not saying absolutely 100% flat, but yeah, it's gonna. Same thing's going to happen with enzyme substrate concentration. Do you expect that the enzyme substrate concentration, do you expect that to hit zero? Give me a number for yes and a letter for no. Ah, good. We've got dissent. And it's not going to hit absolute zero. The reason why not is because what is the system ultimately going to reach? I'll give you a hint. It starts with an E and ends with equilibrium. It's going to reach equilibrium. We're going to have some of that enzyme substrate concentration. We're going to have some of our free enzyme. We're going to have some of our product. We're going to have some of our substrate in there. Is it going to hit absolute zero? No. Is it going to get very, very low? Yeah, absolutely. But that's basically what this graph is showing. If we kind of went on to eternity, this would be our equilibrium, is where it's going to end up. Now, when we look at this graph, one of the things that I want you to be familiar with and thoughtful of is this graph is not, keyword, not a Michaelis-Menten curve. It's tempting to look at and say, aha, that's what it is. It is not. What this is showing is simply the concentration of our different variables and reaction time. Now, jump ahead. Our substrate starts high. Our enzyme starts high. Those other two things end low. What we are interested in is what's known as steady state kinetics. We want to look at our enzyme basically when it's kind of performing optimally. When we have relatively constant concentrations of our enzyme and our enzyme substrate complex. When our enzyme, go ahead.
I'm sorry, it's so hard to like ask a question and not feel like you're interrupting.
No.
Um, I was wondering, so I think I was a little bit confused when we said like what happens over time to E and what happens over time to ES. Would the answer be like they're striving for equilibrium?
Yeah, absolutely.
Okay.
So like on a timeline of forever, that E and ES, they're going to kind of like reach lot. I would say that those lines are going to end up almost parallel to one another.
Okay.
And please don't feel like you're interrupting. And also, whenever I say something, um, and I'm like, do you, yeah, anyway, yeah, so,
Thank you.
good. Okay.
Yes, great.
Okay, so steady state kinetics, that's what we're interested in. And the two people who are credited with really getting a good understanding of steady state kinetics and how an enzyme catalyzes a reaction is I believe is John. I don't know that it's not John. Michaelis is his last name. Um, and I think that they were married eventually. Maud Minton. These are two biochemists that studied enzyme reactions back in the late 1800s, early 1900s. And so they studied steady state kinetics. And whenever it comes to Michaelis Minton kinetics, we're kind of looking at a space like right here, where our amount of our enzyme substrate complex is at its peak and our amount of free enzyme is at its lowest possible. So that's what we're interested in. Now, whenever it comes to studying um, kinetics and rates of reactions, there's a couple of things that we want to do. Now, this right here is your X and Y axis for a Michaelis-Menten curve. I want you to know these because there's another curve we're going to look at that's basically that has slightly different uh, labels for the X and Y axes. Now, in this graph, we are not looking at our free enzyme concentration or our enzyme concentration. Arguably, when we are looking at Michaelis-Menten kinetics and we are looking at this graph, we do not care about that. The reason that we do not care about our enzyme concentration is because it will be fixed. And what I mean by that is when you're studying an enzyme, if you were to, like, let's say a test tube, we're going to have a couple of things go into that test tube. We're going to have, let's go ahead and say 10 nanomolar of substrate. Okay. We have a concentration, we have an amount of our substrate. And then let's say 25, we'll just go with micrograms of protein. Or let me rephrase that, enzyme. Okay, so that's one test tube. And then last but not least, we're going to have buffer. We're going to have a fixed amount of that buffer. And so the amount of solution, that's going to not change. And what we are going to do is we are going to monitor the velocity or the rate that our product is generated. So I'll say product over time. Now our x-axis is going to be labeled as our substrate concentration. Wait a minute. I just said in our test tube, we would have a concentration, a designated concentration of our substrate. I stand by that. Because we're going to be looking at and varying one thing. And the thing that we're going to be varying is our substrate concentration. So this would be trial number 1. Now in trial number 2, we're again going to have a test tube. We're going to have buffer. We're going to have 25 micrograms of our enzyme. So the same amount of our enzyme. And then 15 nanomolar of our substrate. Does anyone want to guess what goes into trial number 3's test tube? We're going to have buffer. I think everyone agrees with that. Tell me about the enzyme and the substrate. Add your mixture to the chat. Good amount of enzyme. I like that. 20 nanomolar of substrate. Perfect. So we are slowly but surely going to be creeping these things up. Now, what that means is our x-axis for our substrate, 0 to, I'm just going to go with infinity. Now, our x-axis is our substrate concentration. Our y-axis is our velocity, so the rate of our product formation. And let's say that I'm going to put some axes or some hash marks down here. So trial number 1, I'm going to go with our substrate here. Let's go with 10, 15, and 20, and then 25. Okay. So our y-axis that's going to correspond to this. Let's say that for trial number 1, we make product. We're generating our with our 25 milligrams of our enzyme. We are going to, and 10 nanomolar of our substrate, we're going to make 5 micromole per second. And let's say actually micromolar, change in concentration per second. So that's our product being generated in a time interval. Can I get a number if, okay, you follow the makeup of trials 1 through 4 and the unit for our velocity, and a letter if you do not follow that? I'm just writing our units there. And then, so this is, I said it was, we're getting it at, with trial number 1, we get 5 micromolar per second. Okay. Then 10, 15, 20, 25, 30. Okay, so my y-axis is concentrations or change in concentration per second. Let's say in trial number 2. In trial number 2, let's say that the velocity or the rate of production of our product is 17 micromolar per second. SEC. Okay. Is that a problem? Let me ask you that. Add a number if you think that's a problem, and a letter if you don't think it's a problem. And spoiler alert, it's not a problem. The reason for that, and I hope this isn't confusing, but your results are your results. And of course, these are made up results, but try not to have any sort of prejudice and go in and be like, no, it should only be this. This is the data that's provided or that's generated. Okay, so 17 micromolar per second for trial number 2, where we were using this. So that's going to be right about here. Trial number 3, where we had the exact same enzyme amount. In trial number 3, we've got, let's see, that would be 20 nanomolar of our substrate. Let's say that jumps up to about 26 micromolar per second. Then trial number 4, where our concentration of our substrate is 25 nanomolar. And then let's go ahead and say that this is, let's say that we get 32 micromolar per second. So I'm looking at that right there. Okay. Now, if I were to, let's see, I'll do one more just for the sake of the illustration. Let's say that this gets up to 35. Now, can everyone take a moment and look at that trend of that data? And give me a number if you think that data follows a linear trend, and a letter if you think, no, it does not follow a linear trend. You're right. It is not linear. Those first few data points you might have looked at it and be like, ooh, kind of linear. But overall, it does not. Now I'm going to flip to another slide, and I want you to give me a number. If you say, okay, yeah, I can see how that trend line applies to this data, or a letter if you say, I don't see that. This is a rough trend line. Give me a number if you see, okay, I can see how that aligns with my data or with the data that we put together. Okay. Now I'm going to go back and just I'll switch colors with the blue. It goes up pretty rapidly and then it kind of plateaus. Now, what does that look like? Spoiler, it's an oxygen binding curve, but for what protein? Close. Give you a hint, it ends with a globin. Yeah, absolutely. And it might have just been my drawing. I apologize for that. But yeah, that looks like a binding curve, an oxygen binding curve for a protein like myoglobin, a monomer. Is this an oxygen binding curve? No, it's not. This is a Michaelis-Menten curve where we are relating substrate concentration to rate of a reaction. Now, thinking about this with respect to an oxygen binding curve and recognizing some of the similarities, well, we had a rate on the y-axis, an oxygen binding curve, we have percent fractionation or percent saturation. We have a maximum. Well, that's kind of a maximum velocity or maximum rate of our reaction. And we use that to evaluate oxygen binding proteins. We do the same thing when it comes to Michaelis-Menten kinetics. Now, if this is a curve for a monomeric protein, do you think that an allosteric protein is going to have a uh, similar kinetic line or similar data set? No, it's probably going to look like the sigmoidal curve of a hemoglobin oxygen binding curve. Okay, so this right here is our overall kind of map for Michaelis-Menten kinetics. Our initial velocity and substrate concentration constitute our y and our x axes. These two numbers, well, they can be variable. The important thing about your velocity is it is going to be a concentration versus a unit time. So something like nanomolar per minute. Sometimes you'll see this written as nanomolar and then minute inverse or inverse minutes. You might see this as molar per second. Your x-axis, that is your substrate's concentration, which is a molarity. This might be picomolar, might be nanomolar. Sometimes, though not often, you might see it written as micrograms per microliter. That is a concentration. Molar concentration is most common, but I want you to be kind of aware of the possibility that it could be a different type of concentration. Now, when our substrate concentration is low, our velocity is also going to be low. As our substrate concentration increases, so data points that correspond to over here on the right-hand side of our substrate concentration measurements, we're going to have a higher velocity, almost to the point where it basically plateaus. Now, with that in mind, here's a curve that I hope looks like to you guys the binding curve, the oxygen binding curve for a protein like myoglobin. This highlights very important points along this curve. This right here is known as a Km. Now, Let me ask you, what on an oxygen binding curve looks to be similar to a Km? P50. Okay. Now, did a P50 have units? Answer yes or no. Yes, it does. Does a Km have units? Yes, it does. Now, a Km has units, and the units are going to be, well, let's jump, they are going to be a molarity, or they are going to be molar units. So, one question that I like to ask would be something like, um, which of the following is falling, bowling? Sorry about that. Which of the following is a an acceptable KM? I've got A, B, C, D. Let's say 13 grams, 4 milliliters, 0.67. Let's go with PL, picoliters. No, I'll change that to PM, picometers, and then 4.2 micromolar. D. D is the correct answer. Now, with that in mind, if you provided your enzyme, or if you provided an enzyme with substrate of 4.2 micromolar, what can you say about that enzyme? Well, what you can say is, so let me write that down. Give enzyme, I'll say substrate concentration equal to Km. Then your enzyme will catalyze a reaction at half of its maximum activity. Can I get a yes or no if you follow that, or a Y or an N? Okay. Now, using this graph, let's say that I give my enzyme substrate concentration. And actually, give me a number. Somebody add to the chat, what's the approximate Km on this graph right here? We'll go with 500. Okay. Let's say that we give our enzyme a substrate concentration of, let's go with 2000. My first question is, if our Km equals 500, would everyone agree with me that in this situation right here that I put my little star, um, I've given my enzyme 4 times the Km? Would everyone agree with that? Give me a yes or no in the chat. Okay, great. What does that do for my enzyme's velocity? How quickly am I catalyzing the reaction? Well, I'm going to switch colors on my pen and I'm going to figure this out. I started right here because that's the substrate concentration I provided it with. I'm going up here. All right there. Okay, so I'm looking at my reaction is being catalyzed at, let's say, 0.28. I don't know what units are defined there, but um, am I catalyzing my reaction at, I'll give you 3 options. Give me a response, A, B, see, at Vmax, below Vmax, and above Vmax. Yeah, B, I am below my maximum velocity. Okay, good. Good. If you understand that, that's a really good position to be in. Now, this gives us two important kinetic parameters. Km, the amount of our substrate needed, or the concentration of our substrate needed to get our enzyme to half of Vmax. And then our other important kinetic parameter, which is Vmax. What is the maximum velocity? Now, if you look at that maximum velocity, where it is on this dashed line, it's about 0.34 or so. That's an approximation based on the trend of this curve. So is this absolutely how fast the enzyme can go? Not quite. It's as close as we can get, though. Now, the Km, or sorry, your Km is your substrate concentration that gives your maximum velocity divided by 2. Do not mistake that to mean that that is Vmax over 2. So whenever you give a Km value, don't say, oh, well, I can just multiply whatever that is. So if I said Km equals 10, don't say, oh, okay, well, that means if I multiply that by 2, that gives me my Vmax. Don't do that. That is a mistake. Now, all of that data, all of that plotting relates to this equation right here.
Can you explain why that's a mistake? I'm not quite following.
Sure. So the the root of that is whenever people say, okay, at its heart, Km equals 10. This point right here is two different values. Think about it like the game of Battleship. This point is a coordinate. It is 10, comma 0.32. So it's a coordination of two different positions. The problem that, or what people always, if I say, I'll give you this curve and I'll say, what is Vmax if Km equals 10? B, C, D. And if you follow this right here, then you would look at it and you'd say, oh, okay, well, 20 is the correct answer. If we look at Km is a definition, we'd say this is 10 right here, this is 20, 30, 40. So it's all about looking at it on a plot or on a graph, where if I said, what is Vmax? And I gave you this graph right here, well, then your Vmax is not something that's going to be found based on your x-axis. Your Vmax is going to be found based on your y-axis. So let's say that this is 0.58. Well, you would look at the graph in order to answer that question. Does that answer your question?
It does. Thank you. I appreciate that.
Sure. So when you have a graph, make sure that you take a moment to look at that and figure out where those points are. Okay, now this equation right here, V sub 0, your initial velocity is equal to your Vmax times your substrate concentration over Km plus your substrate concentration. Now, this is a way to figure out what is the velocity that we're actually going at if I'm provided with, let's say, what my Vmax actually is, what my Km is, and what my substrate concentration is at a given point in time. So this is a way that if I gave you what is V sub 0 if substrate concentration is 9 and Km is 14 and Vmax is 12.2. There we go. If I gave you all those values, you could figure this out. Just plug it in and go. And whenever I give this sort of question on an exam, here's the answer options that I give. Let's see. Two. If I gave this exact situation, let's say, let's go with five. I'll just go with correct answer. Then I'll go with 14.6 and 2.1. Okay. Now, there's a couple of low-hanging fruit incorrect answers on this. If I said, what is our initial velocity? What is our V sub zero? If your substrate concentration is 9, your Km is 14, and your Vmax is 12.2. That's the sort of question that it's not just some abstract, like, let's throw it in and hope we get the right answer. There's a couple of things that you can do immediately. Our Vmax is 12.2. What can we say about our substrate concentration compared to our Km? Well, our substrate concentration is lower than our Km at that point in time. So what are the chances that we are at our maximum velocity? And if it's at all helpful, I'll jump back and look at this. I'll erase some of these points. You're right, it's 0. But let's see. Okay, 12.2, so we're 12.2 right there. Then 14. And our substrate concentration is 9. So if this is 14, we're right about here. Well, this is 6.1. That's our Vmax divided by 2. So this point right here is 14, comma 6.1. Our substrate concentration, 9, being right here. Well, that means that our velocity right here looks to me, I would call it about 4.6. Does everyone follow that? Give me a yes or a no if you follow using this graph from this data. Okay, great. So Michaelis-Menten kinetics is a very important thing when it comes to plotting data and looking at the results of it. Now, I'm going to, let's see. I'm going to jump ahead just so I can come back in a minute. No. I'm not. Okay. So we're gonna take a break for just a moment when we're thinking about graphs. Um, Instead, we're going to change gears a little bit and talk about substrate binding. So we started with the discussion of what's the sequence that substrates follow? Do they have to follow a sequence? Does the enzyme change? Does the enzyme care about which substrate binds? Now, substrate binding sometimes will follow a recognition. So the enzyme will bind to a relatively small substrate through a bunch of weak forces. Now, what are those? Those could be ionic interactions, hydrophobic interactions, some hydrogen bonding. A substrate binding site generally is in a cleft or indentation on the surface of the enzyme that is complementary to the substrate. So what that means is we've got a substrate represented here by this kind of UFO-looking object that, well, it has a couple of exposed areas, maybe a negative charge, and then it's got some candidates for hydrogen bond acceptors and donors. And then here what we have is where our substrate has kind of fit into that groove or that pocket on our enzyme. The enzyme is going to have some complementary regions. So here, hydrogen bonding complements. Then here's a hydrogen bond acceptor. So there are going to be some complementary regions there. So an amino group complements with a carbonyl group. Now, that is going to have some shape complementarity as well as some electronic complementarity. So there are going to be some chemical components of that group or the groups on our small molecule and our enzyme that complement one another. Now, enzymes are going to be very specific, just as I said, or no, sorry. Um, Enzymes are going to be highly specific in that they are going to select for only substrates that they want. Now, with that in mind, there are going to be some enzymes that will be very rigid in what they select and what they bind to, and then there are going to be others that are maybe not quite so rigid. So there are some enzymes that will have just one substrate. There are also some enzymes, and sorry, the ones that have just one substrate, they observe something known as absolute specificity. This catalyzes the reaction of one unique substrate to a particular product. So the input is one specific molecule, the output is one different molecule. So an example of that is the enzyme carbonic anhydrase. You do not have to memorize that name. I'm just adding that to be like, see, it's real. There is also relative specificity. Now, relative specificity is that which an enzyme can classify, can catalyze a reaction of some structurally related substrates to give structurally related products. So, as an example, alcohol dehydrogenase is an enzyme that does that. It takes on different alcohols and converts those to different um, ketones. The structure of substrates matters. There's stereospecificity. When we talk about sugars, you'll get some more context on that. Stereospecificity says that enzymes or they will catalyze reactions in which one stereoisomer is reacted or formed in preference to all others that might be reacted or formed. Now, an example of that is some sugars. I'm getting ahead of myself just a little bit here, and I apologize for that. But there's a biologically relevant form of sugars are known as D sugars. And that has to do with the stereo specificity. L sugars are biologically irrelevant. Um, yeah. So yeah. Geometric specificity is that is selectivity in regards to the chemistry of the substrates. And so there we go. Now, free energy changes upon binding of our substrate to our enzyme. We talked about that Cleland notation, ES and EP. These are temporary or transient complexes of the enzyme with the substrate and the product. Those reversible equilibrium arrows show that the enzyme and substrate complex can form and it can dissociate. The binding of substrates releases free energy, which can be used to overcome transition barriers. Now, how does that take place? What we talked about last week was, oh yeah, the activation energy is lowered. Cool, great, that's fun. But how exactly that takes place is a little bit complicated. Substrate binding. This is one of the reasons that an enzyme is great is that it can lead to, when a substrate binds, there can be an overall reduction in entropy. Substrates are going to be oriented in the optimum way for a reaction to take place. Another thing that an enzyme can do is lead to desolvation or solubilization of a substrate. They can also form lots of weak interactions. Now, in a transition state, this is going to be offset and the substrates are going to be distorted a little bit in order to get closer to that transition state or that end point. So when it comes to entropy reduction, what we have here is a couple of examples of that entropy reduction. So let's see. So our reaction shown here with model A. These two reactants are going to be in close proximity to produce this molecule right here. And an enzyme is going to help out, or sorry, this is just showing that whenever you can lead to something that is a little bit less chaotic, then we're going to see a decrease in entropy. And so there are some instances, some molecules that are going to be in close enough proximity that this can accelerate this reaction at a very high rate. Desolvation is also something that can expedite a reaction or that an enzyme can utilize to speed up a reaction. So here what we have is lots of organization and order of water molecules surrounding a substrate. Then here what we have is lots of water molecules surrounding an enzyme. That substrate basically gets delivered to that enzyme, and then these two things almost become one in some respects. That's our ES complex right there. The last thing that I think is probably the most relevant has three different models. So if we look at the top here, here's our substrate, a metal rod. That's our substrate, that's our input. Our output, right here, a broken stick or a broken metal rod. Now, how do we get from the stick that's intact to broken in half? Well, there's got to be some input of energy. It's not going to spontaneously break. So in order to get this stick to be broken, there's got to be an increase, or there's got to be energy input, which would be an input of energy, which is going to get us to over that hump where the activation energy has been added. Now, if we look at model B right here, if we had an enzyme represented by this blue glob here, and that enzyme were to come around and just bind that substrate, think about this substrate as, think about the enzyme here as basically a hot dog bun. That enzyme fits perfectly to hold on to that hot dog. Our chances of the enzyme breaking that hot dog or that metal stick in half are pretty slim because the shape of the enzyme perfectly complements the shape of that metal rod. So this enzyme is kind of unfavorable. Now, the model that's most beneficial to an enzyme or an enzyme catalyzed reaction is shown here at the bottom. So I want you to be familiar with this one above all else. And think about this when it comes to, an enzyme's supposed to help out. This characterizes that very well. Our blue glob is our enzyme. Now these red lines that kind of surround that opening, think about that as the shape of our enzyme's active site. What can you tell me? Think about, is it different or is it the same? Is the opening region here on our enzyme at the bottom, is it different than or the same as the active site of the enzyme in model B? Add different or the same? There's more space. Yep, it's different. Absolutely. Now, if we look at the top here, we kind of have a sense of the pathway that our substrate has to go in order for it to break. There's got to be some bend to it until it snaps. So it's straight, it's bent, it snaps. Now, in this no enzyme reaction at the top, we're not really sure what's happening, but it's going through that. This right here is known as the transition state. That is represented by this double dagger symbol there. So regardless of if an enzyme is present or not, we go to that double dagger point. We always go through a transition state. If an enzyme is present, great. If no enzyme is present, great. We are still going through a transition state because our substrate has to transition to the product. Does everyone follow that? Answer yes, I follow, or no, I don't. Okay. Now, at the bottom, like I said, this is the part that we're most interested in. This is the one that it's like, aha, an enzyme's doing something. I had a couple of folks who said that the opening of our enzyme right here was different than the opening of the enzyme in B. I agree with that completely. This opening in Model C does not complement our straight stick. Instead, the shape of our opening in our enzyme at the bottom is more similar to the shape of our stick in its transition state, where it's bent. Now, what that is kind of indicating is that if our enzyme is going to bind to our substrate, our enzyme's opening, our enzyme's active site, is more similar to our substrate when it's in its transition state than when it's in its lowest energy level, when it's in its base state. So one way that I think about it is, and I'll use an example here. Got to make sure I use one that's not really worth anything. Um, no, not that. Yeah. No. Okay. So I'm going to use a baseball card. This is my substrate. If I put my hand as my enzyme and I say, okay, well, here's my hand, holds onto the baseball card very easily. Okay. If I change the shape of my enzyme to be like this, or change the shape of my hand, the baseball card, if I put it in this way, it's going to fall right out. What is going to happen or have to happen for my baseball card to fit in my hand? It's going to have to bend. So, what that means, and what I'm getting at here, is the active site of your enzyme is more similar to the transition state of your substrate than it is to kind of the base state of your substrate. Can I get responses on that? Like, yes, I follow, or I don't, I missed it. And any questions, go for it. Sure. So here is my hand as the enzyme. I can hold the baseball card. The baseball card right now is in its opening state, its basic state. Fits perfectly in there. Is this baseball card going to bend in this situation? No, it's not, because my hand has no reason to bend. My hand is good. If, however, I change the shape of my hand and my baseball card, oh, well, it's not going to stay in that way. In order for my baseball card to go into the active site, the baseball card has to bend. So it's almost like it gets forced into fit in that active state, or active site, I'm sorry. So what we want is enzymes that have a active site that resembles a transition state of our substrate. So that's what we're looking for, because then all of a sudden, whenever my enzyme and my transition state form of my molecule is ready to go, then it's just a little bit more small movements and boom, my substrate's been ripped. So there we go. Now, we'll proceed from there. When it comes to, okay, so let me take a moment to give an overview of what we've covered today. We have covered models of substrate binding, where we talked about the sequences. Does this substrate have to bind first and then this substrate when we're talking about multi-substrate complexes? We have also talked about Michaelis-Menten kinetics, looking specifically at your um, substrate concentration, where we were able to use that to determine our maximum velocity and our Km. So the two kinetic parameters that we've looked at are Km and Vmax. Most recently, what we've looked at is, well, when that substrate does bind, what does the active site of our enzyme look like? And the active site of our enzyme resembles a transition state of our substrate. Now, what we're going to do in the next few minutes is we're going to talk about a couple of different catalytic mechanisms. We're going to use this then as a jump off point for tomorrow. Tomorrow, I think we'll probably start maybe around slide 30 and then get through the rest of that. If you want, as kind of a good preview and more time to look at kinetics, slides number 50 through 67 cover the next phase in understanding of kinetics. Slides 50 through 67 talk about a Lineweaver-Burk plot, which is basically taking a Michaelis-Menten plot and making that data linear. Okay, and that would be very helpful for the problem set that you guys have. So I'll do this for the next couple of minutes and then I'm going to call it off. Okay, catalytic mechanisms. In organic, mechanisms were push some electrons, move this electron here, these electrons here, go. Same sort of thing. But the biggest difference when it comes to catalytic mechanisms in a biochemistry class is how are amino acids, which are the parts of enzymes, how are they contributing? So enzyme reactions are described in the same way as non-enzyme catalyzed reactions and non-catalyzed reactions. For example, if we were to have something like an amine react with a carbonyl carbon, well, let's think about this in terms of charges. Partial negative, partial positive. Those things are going to be attracted to one another, in which case these electrons are going to be pushed over there. Amine reacts with an aldehyde or a ketone, and lo and behold, we form a carbanolamine intermediate. That is going to lead to an imine or a Schiff base to form. I do not expect you to memorize this or know this. This is something that if you go on to take metabolism, which I suggest because it's a fantastic class, you'll get into this. You'll learn about Schiff bases and where they are biologically. There are count them, three basic types of enzyme mechanisms. Acid-base catalysis. Give me a number if you think that in acid-base catalysis, protons are involved. And give me a letter if you think, no, protons probably aren't involved. Yep, good, good, good. So in acid-base catalysis, catalyzed reactions, covalent catalysis, where you'll form a covalent bond, and then metal ion catalysis. Yes! Well, we're going to start off with acid-base catalysis. Involves proton transfer. Fantastic. The hallmark of acid-base catalysis is one substance has a proton, another substance picks up that proton. That's at the heart. There is general acid catalysis. In general acid catalysis, a general acid donates a proton to a substrate. So molecule A has a proton and donates it to a substrate. Now, with that said, there's some important pieces of terminology here. The proton is donated to a substrate. So what that means is our enzyme is the acid. Now, with that said, that enzyme is made up of amino acids. So we've got to have an amino acid that has a proton to donate. Add to the chat the single letter code for any amino acid at any pH that could act as a general acid. Okay. I like to think that you were just saying, okay, I'll do that. But you're absolutely right. And I know that's not what you were doing because you were saying lysine. Lysine can absolutely act as an acid. Aspartic acid, histidine, glutamic acid, cysteine, and arginine. These are all great candidates for acting as a general acid. Now, the key is that these active site residues have to be protonated. Aspartic acid, D, absolutely it could. General base. General base catalysis is where an enzyme active site residue must be deprotonated. So again, the same players could be involved in this. Now, give me a number if you think, oh yeah, valine is going to be a great candidate for acid or base catalysis. Valine, starting with the single letter code V. A number if you think yes, a letter if you think no. You're right. Valine's going to be no good because valine's a non-polar residue. This is one of the reasons that the polar residues are so important because they're involved in this sort of stuff. So, last but not least is concerted acid-base catalysis. A general acid and a general base both participate in this reaction. What this means is that I'm going to label it as AS. The active site has one residue that's protonated and one that's deprotonated. So a good candidate for that would be, well, prot histidine and a deprot ASP, aspartic acid. So simultaneously, those two residues, one is protonated, one is deprotonated, and they are going to be involved in this proton transfer. Now, of all of your amino acids that are involved, glutamic and aspartic acid, lysine and arginine, cysteine, histidine, serine sometimes, and tyrosine will participate in this. Most of these are your polar negative, polar positive residues, but there are also cysteine, tyrosine, and serine, which are polar uncharged residues. At the end of the day, what I want you to take away from this is no non-polar residues are involved in acid-base catalysis. I think that it's worthwhile to think about, well, what does that amino acid look like whenever it's protonated, whenever it's deprotonated? We have a little bit of practice with that, but it doesn't hurt to, kind of revisit that subject. Now, what that means is you've got some amino acids where they're pKa. Well, glutamic acid and aspartic acid. These have pKa's about 3. So what that means is that those amino acids, and I'm going to say about 3, those amino acids, if the pH is 7, the likelihood that they are going to act as acids is a little bit low. Is that to say that they can never act as acids at a neutral pH? No, but it's just a little bit unlikely. So more than likely, at a pH of 7, they will act as bases. Okay. Now, when it comes to an enzyme's activity, an enzyme that participates in acid-base catalysis, well, something that is acting as a base, well, its activity is going to be low activity at low pH. Whereas something that a general acid will have high activity at low pH. Now, what this ultimately means is if you have concerted acid-base catalysis, so this is where you have one residue that's acting as an acid, one residue that's acting as a base. Well, the active form of this enzyme is going to have a particular range. This isn't necessarily 3 to 10. That range can vary a little bit. You might have an enzyme where its highest activity is between pH of 3.5 and 4.1. but everything outside of that is going to fall off the table. Because if you need one amino acid to be protonated and one to be deprotonated, and they are both protonated, that enzyme's not going to work. When are they going to be both protonated? At a lower pH. Now, this is where I'm going to stop. This is slide number 29. We'll pick up with slide 30 tomorrow, which is covalent catalysis. What I would stress about today, maybe not stress, let me pick a different word. What I think is an important takeaway from today is zoom out. Make sure that you know those three models: ordered, random, and ping pong. Understand how they're similar, understand how they're different. I think that it's most beneficial to compare ordered and random to one another, and then think about the ping pong model as kind of a different animal altogether. The more comfortable you get with looking at a Michaelis-Menten curve, the better off. If you look at your problem set for this week, there is a problem or there is a question that asks about and gives you some Michaelis-Menten data. You can plot that. And if you want to kind of work ahead, try to convert that to plot a Lineweaver-Burk plot. And then definitely feel like if you're thinking, okay, yeah, that's great, but I need something else. Think about these amino acids, all of these residues, and these definitions. Think about what that means. And just try to kind of visualize like, okay, well, we've got concerted acid-base catalysis. We've got one amino acid that's acting as an acid, one that's a base. Okay, what's a good tandem of those amino acids that are going to do that? Um, and I'm going to go ahead and stop though. I hope you guys have a great day.